Hello there. This is a video that I'm recording today for CTI 120, and we're going to be going over, this is chapter 6 in the book, but it's actually, I think, module 5 in the course material in the modules. And this is on chapter 6 from the book Fundamentals of Communication and Networking. Now, some people have gotten this book from the bookstore. You can also order this book online. You can save yourself some money doing that. You can order a hard copy if you want. If you get a hard copy, the advantage is you can keep this book forever and refer back to it in your later classes as you're taking more networking classes, like if you're working on your CompTIA Network Plus, or if you're going to go for your CompTIA Security Plus. This has a lot of really good information that's going to apply to both of those classes later on. So anyways, let's go ahead and get started into this material. And our learning objectives, we're just going to be talking today about session, presentation, and application layers, which in the TCP/IP model, they just call it the application layer. But they kind of bundle this all together, but the functionality is going to be the same. OSI model, as you know, is just a good way for us to talk about this academically. And so a little bit of communications. Now, this doesn't really have to do with the OSI layer 5. The modes of communication that we're going to be using to get our information from point A to point B is going to be primarily full duplex communication. That's what all of our Ethernet communications are today. Once upon a time, we used to use half duplex. We didn't have really good ways of error checking, things like that. And so what we would do is set up a situation where either you were transmitting data or you were receiving data, but not both at the same time. That's a little bit of primitive communication that you're probably not going to see. Now, simplex communication, this is not really done all that much. Sometimes it is kind of like if you're watching Netflix. Okay, Netflix is an example, kind of simplex communication. You click on a movie that you want to watch, and then you kick back and relax while the streaming service just streams that video to you. So that's kind of like simplex, although not really, because in the background, your communications are going to be using TCP/IP with UDP, User Datagram Protocol. The better example of simplex really is a radio station. So like right now, I'm the DJ, and you guys are listening to this presentation that I'm making, and you can't respond to me because this is a message that I'm laying down. I'm going to post it to YouTube, so later on you can play it back. I'm talking, you're listening. That's simplex communication. And you don't have any way of keying up a microphone and interjecting with a question. Okay, so some common protocols that operate at layer 5. There's quite a few here. But the ones that we're going to be talking about today are going to be this H254, Layer 2 tunneling protocol, NetBIOS, remote call, server messages, and SOCs. These things have varying levels of importance for us. As network engineers, we're probably most concerned with Layer 2 tunneling protocol. But a little bit about these. In H254, this is used in communications like Zoom conferences, WebEx, things like that, multimedia communications where you have like video and audio. Tunneling protocol. This is what we use to create virtual LANs primarily. So this exists at the session layer where with our layer 2 tunneling protocol, what we do is we take one Ethernet switch and then we can divide it up and make it look like it is 2 or 3 or 4 virtual switches, even though all the networks are using the same switch physically. They're using They're using the ports as if they were actually on different switches. So you can take one big piece of hardware like a 48 port switch, and you can divvy that up into like 6 8-port networks if you want to. And then of course you have to route in between those, which we'll talk about in the next chapter. NetBIOS, what this did was it allowed us to share files and printers on a local area network. This is something that we did prior to connecting to the internet. So if you were in an office and you just had one computer that was hooked up to a printer, then you could share that printer out to everybody else in the office, and then they could all print. And that way, you could, instead of everybody having their own individual device, you could invest in one really good color laser jet and just let everybody use it. Remote procedure calls. What this allows you to do is from one computer, run a program on another computer. So this is a way of doing kind of like client-server sharing. Server message block. This is a protocol that allows remote access to devices from one computer to another, similar to NetBIOS. And then SOCKS is used in the event that you have a situation where you need to set up a proxy server. Proxy servers used to be real popular. They're not that much anymore because our equipment has just gotten so advanced. But what a proxy server allowed you to do was have a computer sitting somewhere in the office that had an internet connection, and then everybody in the office could get out to the internet via that computer. Like I said, of these, the most important one for us is going to be the layer 2. Okay, on to the next. All right, presentation layer. Presentation layer provides you an interface from your application layer programs like HTTPS and FTP. The primary thing that we're going to be doing at the presentation layer is going to be formatting data and handling a lot of security protocols. So like if you're using secure FTP to transfer files, then that's where this is the layer at which that's going to happen. And some protocols that you're going to find residing at the presentation layer are things like secure shell, secure sockets, transport layer security. These are methodologies for encrypting data as it's going back and forth across the net. Like for example, if you're doing online banking, all your data back and forth is going to be encrypted, probably using transport layer security. That's what most systems use now. Something else that we are going to see at this layer is Internet Message Access Protocol, and this is used in email servers. Whoops, I didn't mean to do that. Okay, application layer. Now, it's possible that you could use application layer software directly. Like for example, if you pull up a command window and issue the FTP command. Okay, so now you're using an application layer process directly. Most of the time we don't do that. We're using web browsers. And you know how like if you go on, I don't know, you go on a website and it says, okay, click here to download the latest version of our software. And you click on that. Well, what that does, whenever you click on that button, it's going to kick off a secure FTP request. That's your layer 7. Your layer 7 protocol is going to be FTP. But you don't actually have to type in the commands. You just click on the button and it says, are you sure you want to download this? Yes. And then the download commences. So all the real layer 7 commands are being executed in the background for you by the shell that you're using, like if you're using Google Chrome or whatever. And here are some examples of layer 7 applications. So you've got things like DHCP, which is how our devices typically get their IP addressing. So whenever you join a network, your computer sends out a request and it says, hey, I'm here, I don't know where I'm at. Can anybody tell me what my IP address is supposed to be and my subnet mask and also my my gateway? What is the router port that I can use to get out of this network? And the DHCP server, which you've already programmed in advance, has a selection of addresses to choose from. And then it also has a DNS server, probably, subnet mask, and next hop gateway information. And it will download all that to your computer. So if you're using DHCP, you don't have to worry about typing in an IP address every time you join the network. File transfer protocol, we just talked about. Hypertext transport protocol, HTTP and HTTPS, which is the secure version of HTTP. Those exist at layer 7, and I know y'all are familiar with those because we've all been surfing the web since we were kids at this point. Network file system, that allows you to pull up a list of files to choose from on another computer. It'll allow you to do things like, okay, do you want to download this for Windows 10 or Windows 11 or some previous version of Windows? Do you want 32-bit software or 64-bit software? It'll give you a list of files that you can pick from, and that happens via the NFS protocol. Real-time transport protocol is similar to FTP, and what that thing does is it defines packets. It's for like streaming media. So RTP is what you would probably use if you were listening to Spotify or something like that. Excuse me. SIP, the Session Initiating Protocol. This is one that's used in like for multimedia presentations. SMTP, the Mail Transfer Protocol, this is used by pretty much every computer. So if you're getting ready to send an email message to somebody, then you're going to be using SMTP to transmit that message. Network Management Protocol is a small protocol that's used generally just by devices to communicate with one another. So I can set up an application on my computer that, say, it monitors the network, and every once in a while it'll send a message out saying, hey, everybody report your status back. And so your switches will say, okay, well, I'm up. Your router says, okay, I'm still here. Your servers send a message saying, I'm still here. In other words, these are just really small managerial type messages that primarily devices are using to communicate with one another. And then Telnet is a program you can use to open up a session to a server. So like say you've got an Ubuntu server running and you want to issue some commands remotely to manage your server. Then you might telnet into that server and open up a command window, a terminal window, and then you can issue your commands as if you were sitting at the console of the machine itself. Now, the thing about Telnet is we don't typically use that anymore. You don't want to set this up in a commercial environment for sure, because it transmits user IDs and passwords in the clear. So if anybody's got a tap on your line, then they can find out your login information, and they can also see exactly what commands you're issuing. So yeah, you don't want to use that if you don't absolutely have to. But once upon a time we used Telnet all the time because we had network connections that were closed or relatively closed, and so we didn't really worry about outside people hacking into our system. But nowadays everybody's on the internet, and a lot of hackers are on the internet, and so you don't want some joker from Moldova using Telnet to access your routers. Okay, application architecture. Now, a lot of times, and this is kind of, I don't know, I think this is being a little bit backwards. We're at the user interface. We're making requests for our processors to access data for us, to pull out some data storage. Like, say you're doing something as simple as just like shopping on Amazon. And from the user interface, you say, okay, show me the latest Brooks running shoes. Okay, well, the processing is going to format your request and generate a data access request. And then from data storage, we're going to pull out all the information we have on Brooks running shoes. And then we're going to pass that data back through these applications, and then ultimately back to the user interface so that you can have a list of what's available. Okay, some different some different applications that you might run into, application architectures. And these are generally, this is stuff that you use every day. You might just not really realize what you're accessing. And like with host-based architecture, when this says host-based architecture, it's not talking about because usually we think of host as being just like a PC on the network. But this was where you had like a central mainframe that it had not only the data storage, but also it ran all the applications. And then we would have what were referred to as dumb terminals connected to the mainframe. And so every time you issue a command, you're not actually running anything. You don't have a workstation per se. All you have is just a window into the mainframe. And so this was not very scalable, but it was what we had to use back in the 80s. And then we came along with client-based applications, in which case now we've got like Microsoft Word and we've got Access and we've got PowerPoint all running on a workstation that's actually sitting in our office. And then those applications can pull data from the main server as they need to. But what this wound up doing was offloading the application processing from the server to the client. Now, cloud computing is kind of an advanced version of that. With cloud computing, you've got a central server somewhere. Like say, for example, Google Mail. That's a really good example of cloud computing. Okay, so Google Mail resides on a cloud, worldwide. And whenever you want to access your mail, there's a central repository, but you actually are running the application level stuff from the browser on your desktop. So you go into your browser, you go into Google Mail, and then you pull up your inbox, and it sends out a query. It says, okay, show me any updated, because the messages, a lot of them are already stored on your local computer. But whenever you access your inbox, it's going to transmit data from the server to you. So now you see, oh, okay, well, I've got 5 new messages in addition to the ones I already knew about. And the good thing about cloud computing is no matter where you go, like say you leave tonight and decide you're going to go hang out at the Cherokee Casino, and you get to your hotel room and you hook up to the Wi-Fi and you can access your Google Mail just like as if you were sitting in your classroom or your office. Peer-to-peer communications, these are typically done for file sharing purposes. Like if I've got a bootleg movie that I want to share, excuse me, well, I can't very well put it out on a server because I'm going to get all kinds of copyright violations, and that's not going to work out too well. But if we both are running peer-to-peer service like LimeWire or BearShare or something like that, then I can actually let you pull files off my personal computer and load them onto your computer. So that's direct communication from me to you without having to go through any intermediary other than the internet. And this is a good time for us to use encryption and point-to-point protocol. Okay, this N-tier application architecture business, the reason why there's an N here is because we don't know exactly how many tiers are in here. It depends on, how big the service is. Like, Amazon, they have a boatload of devices that are doing nothing but serving out web requests. And then I don't know how many application servers they have, probably quite a few. The application server is actually doing most of the work typically. So the way this thing works, and this would be a 3-tier model, actually a 4-tier. Okay, so here we are, and we're making a request to, and it doesn't have to be Amazon, it could be any old company that you want to look at. So the web server is going to present you with the web pages. Okay, here's our storefront. And then once you decide that you want to look at something, then you're going to go through the application server. And the application server might be handling things like credit cards, any information that you have, because some places will they'll say, do you want to store your credit card for future purposes? So they would have an application server that handled credit card requests. And then back here we've got a database server And the database server, its job is to answer requests from the application server and do accesses to the database. So this is actually the machine that's going to be looking up information in the database that's hosted on yet another computer. And so, you make your request. Okay, do you have this item? Okay, going to pass that request on to the DB server. DB server is going to query the database and say, hey, do we have these items in stock? Yes, we have the following items in stock. Pass that back through. Okay, do you want to purchase this? Yes. Okay, we're going to handle that through the application server. So you can see how the main reason why we're doing this is because we don't want to have just one computer that's handling everything. If we've got one machine that's having to answer web server requests and handle all the applications and also do our database queries, well, that's going to have to be a big honking machine with a lot of processor power. And no matter how big it is, if you get like 6 million users on board, it's going to be brought to its knees. So you have to distribute the load out over as many computers as you possibly can. All right, so some features and benefits of host-based, client-based, client-server. Now, host-based, it was pretty easy to maintain security because you had a systems administrator and he got to say who can access this computer and who can't. And we didn't have to worry about anybody running applications on their computer. They didn't have a workstation, so they couldn't run any applications except for what were written on the mainframe. And then client-based, that brought a lot of the load off the server and out to the desktop. The problem with this is, okay, if you've got narrow, like if you don't have good network communications, then this can be really slow. Client-server, this depending on how much data you're talking about, performance can wind up being slowed, but client server does actually scale pretty well. And then our cloud computing scales the best. If we need to service clients all over the planet, then this is definitely the way to go. What N-tier architecture allows you to do is have multiple servers, and you can have tasks divvied out to different servers. For example, you might have one device that was tasked with managing credit card charges, and then you could have another device that was your inventory management. And these devices all talk to the database serving devices, which actually are in charge of shuttling data back and forth from the hard drives to the systems that need the data. And so you can have, different devices for different applications and all share the same common database. And this is the kind of architecture you're going to find at an outfit like Amazon, other online retailers, Newegg, places like that they maintain databases not only of their inventory, but also their customers, what the customers ordered in the past, what they might be interested in now, so that you can do like suggested emails, stuff like that. Now, P2P computing, peer-to-peer. Peer-to-peer doesn't have any kind of central server involved at all. This is file sharing programs primarily, where I can have files on my computer and you can have files on your computer, and we trust each other, and so we share our data back and forth. Now, the problem with this is you have to trust the other people that are on the P2P network, because there's not going to be any central person, that's going to be doing any kind of login information or verifying that files are safe. So you could accidentally be sharing out viruses and Trojan horse stuff, without even knowing it. Or if you're a malicious actor, you could join a P2P network and offer a bunch of videos, photos, whatever, and embed your own malicious code. Okay, let me see if I can get this mouse to work. Here it goes. Okay, now the next thing I wanted to talk about just briefly is this business of aligning your task. And we were talking about this in class. Okay, say you've got a business issue, like your boss comes and says, I want to make sure that every device on the network and every server, I want everybody to have 1 gigabit end-to-end connections. Okay, cool. Well, the boss has just told us what he needs. Now, how do we make that happen? Well, it could be that all of the devices on the network already have gigabit Ethernet support natively. But then we have to look at our switches. You know, do we have switches that will only support fast Ethernet? Well, if so, we've got to swap those out for gigabit switches. Or we have to consult the manufacturer and say, hey, is there like a firmware upgrade or something that we can apply that will enable our switches to communicate at gigabit speed, right? And what about our router interfaces? What about our interface to our ISP? You know, do we have gigabit everywhere? Well, we don't know. What we're going to have to do is go and inventory all of our equipment and figure out what can support the network at the speed we're talking about and what can't. And then we go to our boss and say, look, we can do everything you want to do, but except for we're going to need $300,000 worth of updates, upgraded softwares and new devices. Do you still want us to do this? And if the man says, yes, I'll write you a check for the 300K. Well, okay, then we get to start placing orders. But then the boss might say, well, no, what's the best you can do with the equipment that we currently have? So anyway, that's how we try to align our architecture. Do we want to do, do we want to manage our own client server architecture in-house? Or do we want to outsource some of our tasks, maybe to a cloud service provider? And, we try to come up with the best solution we can and tell the boss what it's going to cost. Okay, now ports. Every application that's internet enabled is going to have a port assignment. So whenever you contact a web server, not only do you need to have the IP address of that web server, you also need to know what socket you're going to be talking to or what port you're going to be talking to. Sometimes I'll use these terms interchangeably, but really a port is the port assignment is assigned to different layer 7 applications. Excuse me. And a combination of an IP address and a port assignment is what we call a socket. So if my address is 192.168.10.5, right, that's my IP address, and then a colon, and then port assignment 443. Well, that means go to this IP address and make a request on this port. And that port is assigned to HTTP secure, right? So depending on your particular application, you may have some ports disabled, and that can be a really good security measurement. So some places say, well, look, we're gonna deny all ports. This is why, if you go to ping a device, it may not answer your ping because they have ICMP disabled on that device. Doesn't mean the device isn't alive and well. It just won't answer ping requests, but it will answer HTTP requests. And here are some ports that you're going to see that are very, very popular. FTP, which we talked about earlier, that uses ports 20 and 21. It uses port 20 for its data streams in and out, and it uses port 21 for the FTP commands. So if you say FTP get or FTP put, then that's going to use 21, but then the data itself travels on via port 20. Secure Shell uses port 22. Now, if you got, say you don't want anybody to be secure shelling into your device for whatever reason, then you can disable port 22, and if anybody tries to make contact with that port, they'll get denied. They won't be able to get in. So this is a good way to protect your system. Port 80 is HTTP. Not very many sites use this anymore. HTTP is not secure, and so therefore people don't want to use it. Instead, they use port 443 for HTTPS. This is secure. This uses transport layer security or socket security in order to encrypt your data so that people can't read it. But these ports are all well known, okay? Nobody is going to have a PC using port 80 or port 161. Okay, web browsers. Whenever you are on the internet these days, once upon a time we didn't have good web browsers, so we used FTTP and things like that just directly. But now everybody has web browsers on their desk, and so regardless of what you're doing, whether you're downloading files or sending an email or whatever, you start with a browser window, and then you bring up your email or whatever it is you're going to do. Now, HTML, hypertext markup language, this is the syntax, the programming language that is used to describe web pages. And any live links on that page, like anything you can click on and go to another page or go to another area of that page that you're already on, these are hyperlinks. Now, URL, Uniform Resource Locator. URL is the common name, like for example, www.cfcc.edu. Okay, that's our URL. But what that translates to is the IP address of our main web server. So that way you don't have to remember all the IP addresses, you just have to remember, cfcc.edu. You type that in and it by default takes you to www.cfcc.edu and you see our homepage. And whenever you're making HTTP requests, your request is really small. It's just like, okay, get this page. So just a little bit of data goes out. And then DNS translates example.com to an IP address. And this is a browser request, and it's an HTTP browser request. So this is going to request example.com port 80. And we go out there, and if there is such a file, such a web page, then it sends it back to us. Now the web page coming back is going to be huge. And in the face-to-face class, we were talking about this. When you send a GET request, that's small, but when the data comes back, it's a lot. It's pictures, videos, whatever. Lots of data. This is why most people at their house have what's called an asynchronous connection. And you can go to a site. If you want to test your internet connection at home, hang on a second. Let me do this. There is a site, www.speedtest.net. Okay, this is an internet speed test you can use, and you'll see what I'm talking about because it'll measure your download speed, and then it'll also measure your upload speed. And like at my house, my download speed is over 400 megabit per second, but my upload speed is only 12 megabit per second. So I can pull files down way faster than I can send them. So if I'm uploading anything, it takes a minute. Now, if you have a business, like here at CFCC, I guess we could kind of be considered a business. We have our own servers in-house. So people are logging into our servers and they need data. So we have to be able to push data as fast as we can get it. And so our connection here is synchronous. In other words, we can send data as fast as we can pull it down off the internet. But, you can get that at your house if you want to, but it costs extra money. All right, now security. I know we're going to have a big unit on security later on in the semester, but for right this minute, security concerns that typically will reside at the application layer. You're going to find things like Trojan horse, spyware, viruses, and you probably know a little bit about these. Trojan horse is subroutines that are built into an otherwise, maybe useful program like a game or some utility that you've downloaded, but there's also code in it that does things that you might not want it to do. Malicious software could be embedded. Now, spyware is a kind of malware that resides on your computer, but it tries to keep a low profile. Spyware does not want you to know it's there. And what it does is it basically just sits there and runs as a background process. And anytime it detects something on your computer that might be a social security number or a credit card number or a bank routing number, then it's going to report that back to the person that wrote the spyware. So it's a good way to harvest data without people knowing you're doing it. Viruses, you guys have probably seen lots and lots on viruses. These are subroutines that are embedded in code that replicate themselves. In other words, they copy themselves into other pieces of code on your computer. Worms are different from viruses. A worm doesn't require you to actually execute a program. What a worm does, and typically the way you'll get a worm on your machine is by phishing. Like somebody will send you an email and it'll say, hey, check out this link. And you click on the link and it might take you to something that looks legit, right? But what you've accidentally done is install a worm on your system. And a worm is a little program that runs in the background. And once it gets started, then it doesn't need any further input from the user. It just sits there and it might replicate itself and send itself out to your contacts, or it might reach out on the network and find out, other devices that are on your local net and replicate itself out to them. So a worm can really cause havoc on a network. Ransomware is a kind of a malware attack where you go into somebody's, again, you get your software on board their system by whatever means necessary, and then it goes and finds database files and encrypts them. And then you have you send a message to the people that you're attacking, and you say, hey, you got to put like $1 million worth of Bitcoin in my account, otherwise your files are going to be permanently encrypted. And a lot of times companies that get ransomware attacked, they do not want anybody to know about it. So a lot of more ransomware attacks happen than you are made aware of, because these are generally kept on the QT, because no company they don't want their customers to know that they've been compromised. Denial of service attacks, what these are is like repeated ping requests or something along those lines that will slow down a server or slow down a network. Distributed DOS attacks, this is where you've got control of multiple computers and you tell them all, okay, all at once, everybody starts sending requests to a server, and you can basically bring it to its knees. And why would you do this? Well, just mostly maliciousness. And then botnets. I've got a really good video on botnets that I'll show you guys later. And a botnet is a network of computers, and they don't even have to be in the same location. They could be all over the world. But these are computers that you've infected with your malware, and you have the ability to remote control those computers anytime you want to. So you can make all the computers on the network, say for example, you can make them all send out phishing emails if you want. And like from your computer, you might be able to send out like a few thousand emails a day. But if you have 10,000 computers all sending out emails, then you might be able to hit, 1 million or 2 million people a day. Maybe more than that. And I don't know if this is going to play. It should. Let's give it a whirl. This is kind of a fun little video that I was going to show you guys. Will it play or will it not? Oh, this looks like a fun game. Delta Force, eh? I might have to try it sometime.
Why does this Worms and Trojan horses are all malicious programs that can cause damage to your computer, but there are differences among these two. What is a virus? A computer virus attaches itself to a program or file, enabling it to spread from one computer to another, leaving infections as it travels. Like a human virus, a computer virus can range in severity. Some may only cause mildly annoying effects, while others can damage your hardware, software, or files. Almost all viruses are attached to an executable file, which means the virus may exist on your computer, but it actually cannot infect your computer unless you run or open the malicious program. It is important to note that a virus cannot spread without a human action, such as running the infected program. So, what is a worm? A worm is similar to a computer virus by design and is considered to be a subclass of virus. Worms spread from computer to computer, but unlike virus, it has the capability to travel without any human action. The biggest danger with a worm is its capability to replicate itself on your system. So rather than your computer sending out a single worm, it could send out hundreds or thousands of copies of itself, creating a huge, devastating effect. One example would be for a worm to send out a copy of itself to everyone listed in your email address book. Then the worm replicates and sends itself out to everyone listed in each of the receiver's address book and continues on down the line. Due to the copying nature of a worm and its capability to travel across networks, the end result in most cases is that the worm consumes too much system memory or network bandwidth, causing the web servers, network servers, and the individual computers to stop responding. So what is a Trojan horse? The Trojan horse at first glance will appear to be a useful software, but will actually do damage once installed or run on your computer. Those on the receiving end of the Trojan horse are usually tricked into opening them because they appear to be receiving legitimate software or files from a legitimate source. Some Trojans are designed to be annoying, like changing your desktop, adding silly active desktop icons, or they can cause serious damage by deleting files or destroying information on your system. Trojans are also a backdoor on your computer that gives malicious users access to your system, possibly allowing confidential or personal information to be compromised. Unlike viruses and worms, Trojans do not reproduce by infecting other files, nor do they self-replicate. So that's all about viruses, worms, and trojans. If you like this video, please give it a thumbs up. For more such videos, just hit the subscribe button or check out my YouTube channel. And as always, thanks for watching.
Okay, so a little bit about the difference between viruses and worms and Trojan horses. Now, what can we do? Well, for one thing, we can keep antivirus software running on our computer at all times. There are such things as real-time protections so that if your computer sees something that looks suspicious, it'll just automatically quarantine it. A lot of times, real-time protection comes with a cost. So, like if you have Malwarebytes, which is a really good antivirus software, just the freeware version will not have real-time protection. You'll still be able to scan your system on occasion, but it won't actively watch for malicious software. Now, using Secure Shell, like if you're going to log into a router or switch or a server to do any kind of maintenance tasks, always use Secure Shell instead of Telnet. Telnet sends its information without any encryption. So definitely use SSH. Now, pretty good privacy. This is a way that this is an old email encryption, but it's effective. It's used in most emails. And then there's also a secure multi-purpose internet mail extension, this SMIME. This is like a better version of PGP. It uses those certificates for authentication. All right, so that basically brings us to the end of this chapter. And so Yeah, networks. Networks allow us to share resources, very, very valuable. Computers nowadays, you would never find standalone computers unless they were just very specialized. Everything we do now is over the net. Okay, so that's pretty much all there is for this chapter. And so I will see y'all again in the next one. I'm going to start trying to do these for every module as we go along, which, hopefully if I walk you guys through these presentations, then, maybe it'll help you remember things a little bit better.